Blog Talk Radio.
Hello, and welcome to the second April 14th broadcast from the Kentucky Waterfield Museum. We have with us tonight for the fourth time Stephen Meyer, a very special guest who's very graciously helped us out by making repeat appearances on this program to share enlightening information about water fuel technology. And let's see if Stephen's not with us. Are you there?
I'm here. Can you hear me?
Great. Thank you.
How you doing?
Thank you for being with us again. How are you?
Great. Say, what does YTBA stand for?
YTBA, yet to be announced.
Oh, okay.
At least I hope that's what it stands for. I hope it doesn't have some other meaning. But, yeah, that's because we have some tentative guests lined up for the coming weeks but haven't confirmed their involvement. So.
Okay. I'm just curious what that was.
And the whole thing is rather confusing. What it gets down to is that the blogtalkradio.com website only allows 5 shows to be viewed by the listening audience as in the archives. And so I decided that some of the information that's contained in the previous programs is important enough that it shouldn't be taken out of the public, their ability to listen to these shows. So I decided to start a new show. Since it's free to do these shows, which is quite amazing, I figured that it's probably best to start a new show with a new name every 5 shows and allow these archived shows to be accessible.
There you go. Okay.
Now, this is a new thing, and they're constantly upgrading their technology. So it's probably going to be possible to merge all of these shows into one archive that is going to be able to be replayed at will in the future. And
oh, great.
I've asked them to look into doing that, and I think they will. But in the meantime, what you have to do is basically go to blogtalkradio.com and do a search on Water Fuel Museum, and you'll see that there are several programs, each of which has 5 archived shows from the past.
Super. Okay. Great.
So in the case of future shows, I do have some guests coming up that everyone should be very interested in hearing from, such as George Wiseman from Eagle Research.
Okay.
And so we weren't able to coordinate that for next week, but rather for the week after.
Okay.
But I'm glad to have you with us tonight. I think we'll probably cover some important ground this evening.
What's George Weissman's background? Does he have a web address, or you know?
Yeah, I believe it's eagleresearch.com.
Oh, Eagle Research.
And he sells books that he's written about water fuel technology, Brown's gas, especially even a book telling you how to build a Brown's gas welder.
Oh, super.
And Water is Fuel is the name of 2 of his books, I think Book 1 and Book 2. He actually sells some products, such as a device to tweak the electronic fuel injection system in a vehicle, so that when you're using a hydrogen-oxygen booster, you don't have a reading from your oxygen sensor that causes the engine to dump more fuel.
Oh, I got you. Okay.
And so I think he calls it an EFI control device. Anyway, I'll look forward to talking to him in 2 weeks and finding out some of these things. I don't know a great deal about his background, so it'll be very interesting to hear from him.
Absolutely. I'll do a little research because I'm curious too.
I do know from another interview we did with Chris Patton, the film producer, who actually videotaped interviews with George and use of the Brown's gas welder and whatnot. He commented on George's having used the Brown's gas torch to separate gold in the gold mining camps in, I suppose, Canada.
Canada, sure.
Yeah, the properties of the hydrogen-oxygen flame were appropriate for separating the gold, I guess, turning it molten and causing it to drip out of the rock or something.
Well, that's interesting, because gold normally is 6 to quartz, and when you find gold, it is typically embedded in quartz, so you would have to heat it and then have it kind of wick its way out of the quartz.
It sounded like that's what they were doing.
Yeah, the only problem you have is that I don't think you can, some of the quartz up in Canada and so forth the gold is found in particulates. They look like black sand, if you will. And when you look at the quartz, it's very small, and the gold is stuck to that. And so if it's in that form, it's a little bit of a problem because as the gas comes out of the torch, it blows it away. So you have to come up with some methodology to heat it and get the melting process without getting that the force of the flame pushing it out of the way. But it can be done.
Now, speaking of gold, what about the use of gold in some of these electrolysis, using it for cathode, anode, or something? Is there any advantage in that? Is there?
Yeah, it's a little expensive. Actually, the electrodes in the processor is very, very important on what's selected. And, when Stan was doing his research on materials, he tried a lot of different things. Like if you would, for example, use brass tubes, for example, and you would put them in, submerge them in water and then put the signals to that, those brass tubes would just absolutely melt away. They would melt down
and not because of the presence of electrolyte.
No, if you just put it in regular tap water, what happens is that the voltage actually is pulling out and breaking down the atoms within that alloy, and brass is really easy to break apart.
So it wouldn't have to do with the fact that you'd be using potassium hydroxide or some other caustic.
No, you can do it in plain water.
And it would still attack the.
It would still attack because the brass is easier. The voltage actually does the work for you, and that's the point. One of the things that I want to bring out is, when they invented the transistor back in the 1950s, when Shockley and his crew at Bell Lab was working on the transistor, they had done some research, and there was a scientist up in Chicago, Enrico Fermi, for example, where he was working up in Chicago, and he set up an experiment underneath the stadiums there, the football stadiums in Chicago. And what they were trying to do, they've been working on trying to split the atom, if you will, and they hadn't done it, and they theorized it. But what they did do, Enrico Fermi, what he did was he was able to do the first split of the atom, and he came up with a proof of concept and feasibility. And what they had done was that they had theorized that radioactive materials like U-235 and U-238, those materials are decaying, and so and are also very massive elements that you're dealing with. Now, one of the elements is found on Earth. It's found, but it's very rare. Typically, the Earth, when back 4.5 billion years ago and so forth, we had really hot spots in radioactivity on the planet, and then as the half-life continued on that uranium, it would break down in what they call a half-life, where the radiation intensity would drop in half. And what happens is the radioactive material actually wick its way down and adjust itself down to lead. That's the end result of radioactivity. So, but they did have samples. Madame Curie and her husband worked with samples of uranium, and they went through just tons and tons of earth, and they finally, after 2-3 years, was able to get 10 or 15 grams, or whatever it was, of this radioactive material. And so what Fermi was doing was that he was trying to come up with a methodology to split that atom, U-235. And what had happened was they had put underneath that stadium, they had huge blocks of beeswax because they found that beeswax and table salt stops the radiation. And then what they realized was that they were bombarding the uranium with protons and neutrons and electrons. Now, the nice thing about neutrons is that it's not affected. So, like you were talking about gold on an electrode, effectively it's very inert. There's not very many things that really attack the gold. You can wear it off mechanically, but not too many things. You can electroplate gold. And so what Enrico Fermi did was they realized that these neutrons that they were shooting at the atoms trying to get it to split was going too fast. It would go right through the atom. And so they needed some methodology to slow it down. So they actually used carbon block material, and they could actually shoot the neutrons into the carbon, and carbon would, what it would do, the molecules would cause it to ricochet within the block of carbon and effectively slow down that neutron. And then what it did was it would slow down enough that when it got to the atom, the atom would have accepted at that point, and it would be like a blanket that covered that atom. And then shortly thereafter, the atom became very unstable because it had that extra neutron in there. And then it would start to fall apart, and that's when Enrico Fermi noticed that he had proof of concept that we could actually split that atom.
Now, does this have any relevance to breaking the water molecule down?
Yes, it does. I'm getting there, I guess. Okay, so the point is this: is that Fermi made his mark in his name to fame, and his name landed in a lot of different places. And one of the places that it landed in was in metallurgy. When you look at metallurgy, they were trying to understand about how the metal was designed and what it consisted of and what was the bands of the atoms that were in there. And so he realized that there was a band of electrons within that metal that float. It floats within the metal, and they're kind of free. They just kind of meander back and forth within that metal, and there's a band, and there's a lot of them. So going back to the invention of the transistor, where Shockley and his group had worked on it for years, and they knew that this band existed because of Fermi's research, and they were trying to figure how could we get to those free electrons, in that material. And they tried for a year about every experiment you can think of, and then finally there was a mistake. And that mistake was that they had taken silicon. If you remember on the last time we talked, I was indicating about the transistor radio where we built those little crystal radios with a cat whisker, right, and that you could adjust it so you could hear the radio. Well, they knew that it did that, but how? Why? How could they get the advantage of that? And what happened was that they were working with germanium, and germanium is a material that has a very low voltages, like 0.23 volts. And they were trying to get to it, and they drilled holes and put probes in and things of that nature. Wasn't having too much success, and then a mistake was made, and that mistake was that an oxide would form on the germanium, and they were cleaning that off with water. And what happened was, one particular time, they forgot to dry the water off of the germanium. So when they put their probes in, the probes went into the water. And voila, they had a signal show up on their oscilloscope. It was a blip. And they said, what is this? And so they further went into it and found out that some reason that when the water was on the germanium, they could put the probe in the water and then in turn would break down through the barrier into the germanium and get to this Fermi layer. And so that's how the transistor was invented. The fact that the water wasn't really a good final solution because it would evaporate and so forth. So they had to find out now why it did that, and then they were able to analyze the germanium, and they found that there's a junction that elements within that particular material would form a junction. So by biasing the junction, you could control the flow of the electrons through that material, and so the invention of the transistor was made, and Shockley also developed the silicon transistor, which was a much better type transistor. So let's bring us back in focus to the water fuel cell that Stan and I worked on. We were trying to select a material that would do just that. What I mean by that is that the stainless steel tubes that everyone's using is a very interesting product because it's not made like you would think iron is made. Stainless steel, it consists of chrome, about 18%. It consists of about 8% nickel. The rest mostly iron. But it's a doping process. And we realized at that point that the doping process of that metal had a lot of had a lot of symmetry of transistor technology.
So in other words, you're using the metal in stainless steel as sort of a transistor? Or?
You can look at it that way. What we realized was that the water that makes contact with the metal sets up a barrier. It's a barrier technology that we realized that was an important part of the cell, as well as the fact that the metal itself has it has a structure that is more conducive to the water.